Two. Good. So yesterday we decided, let me mute this for a second. We decided that the chance of getting heads on a flip is 1 in 2, 1/2. What does that mean? What does that mean? If you had to explain that to someone, what does it mean that the chance of getting heads on a flip is 1 in 2? Or a chance of tails for that matter. That's what Dai just said. The chance of tails on a flip is also 1 in 2.
Both sides have an equal chance of winning.
Ah, okay, good, good.
That there's 2 options and what you're looking at is one of the 2 options.
Good! Can I insert 2 words in what Andrew just said? First of all, what Nick said was, actually wait, what did you say, Nick? Because it was correct.
Both sides have an equal chance.
Both sides have an equal chance. That's what I wanted to insert into what you said, Andrew. You said there are 2 options. The kicker is they have to be equally likely in order for that to be true. Because there are also 2 options. I'm going to give you an example from my own personal experience. I sent Max in to High Desert Ranch at home 3 years ago with a little tiny cardboard box. I said, go pick 4 baby chicks. Start a chicken flock. Go pick 4 baby chicks. And he walked into the bins and he grabbed an Americana, and he grabbed an Orpington, and he grabbed the Plymouth Barred Rock, and he grabbed the Delaware. We're going to study these at 243, those you take me for 243. That's also a coin flip if you think about it. Because each of those little chicks he buys is either a girl or it's not. It's either a girl or it's not. And when I went to the top, I went to the bench and asked the guy, because this thing's like this big when you buy them Dales, they're this big, they're tiny. And he said, female. I'm like, how the hell can you tell they're female? Because there's a bin of boys next to him that look exactly the same. He's like, oh, he sexed them. With their skirt? How do you sex a day-old chick with this big? He's like, oh, we've got methods. I'm like, okay, well, how good are you at it? And he said, we're 90% accurate. That's a coin. That's a coin. Because you get a girl or you don't get a girl. But the thing about the coin, that coin is it's not equally likely. You don't say it's 1/2, you say it's 9 in 10. So it's still 2 options, like it is for this. But the kicker with 1 and 2 is, yeah, that means they're equally likely. They're just as likely to get heads as tails. That isn't the way it works with chickens. Or, for example, I think I mentioned this to you, speaking with someone about, why do you ride a bike? And I said, well, why do you drive a car? And they said, well, you got such a high chance of dying riding a bike or crossing the street. They said, it's 1 and 2. Time out. 1 and 2. Well, 1 and 2 because there's 2 options. You either die or you don't. But they're not equally likely, yeah? That's the whole point. So that's why I keep putting that word equally likely in there. Good. Say it a different way. How would you explain that to a gambler who needs to flip heads on his next flip?
50-50.
It's 50-50. Explain it to him. Well, what does it mean to be 50-50? He's got all his money in his pockets and he's betting $1 a time, and every time he's betting $1, right? And every time he flips heads, he loses his $1. He doubles down his bet again. And then he flips again, and if he flips heads, he loses that, he doubles down the last bet. And he keeps flipping until he gets tails. How do you explain to him what that means?
He's going home with a barrel.
Well, he's going home with $1 eventually. He's going home with $1 eventually.
50%.
But it's going to take him a lot of money maybe to get there. 50% of what?
100%. Right.
50% of what?
The time.
The time, what happens?
You're going to get the thing that you want.
Good. That's the way I want you to think of it 2 ways. And the reason I want you to think of it 2 ways is, thank you, Benji, and thank you Nick and Andrew for giving us both ways. This 1 and 2 equally likely bit is perfect because it means there are 2 outcomes, equally likely outcomes, and we end up getting one of the outcomes being heads, the other one being tails. It's perfect. It's absolutely perfect. The trick with it is that means over time you're going to see heads half the time and tails half the time. When are you going to see heads and tails? So here comes classic story. Hey, hold that thought. Classic story from my statistics class in college. My second statistics class, 371. Vince Larisha, love you, Vince, if you're watching this. Said he used to follow his favorite college sports team. And they do a coin flip beginning of every game to decide. Hassani mentioned the coins are very, very large for the college games. I guess you have to see them with the cameras from far away. I don't know. Or who knows why. But the point was, he said he watched his favorite sports team flip, I think it was 8 times during the season, and every single time the coin was flipped for them to call, it came up tails. And his next question was, if it's come up tails 8 times, what's the chance of tails on the next flip? Right, which we all said. And he said, yep, but I bet on heads. I said, Vince, why would you do that if it's 50-50? And then he backpedaled. He backpedaled because he let human nature kick in. Human nature says if you see a string of tails, you're going to see a heads next. Now you saw what happened yesterday when we had that board full head H's and T's, yeah? There's no discernible pattern whatsoever in when the heads and tails show up. The only pattern is what? And how much of each? Roughly 50-50, and the more you flip, the more the 50-50 shows up. Thank you, Micah. Exactly, thank you, Di. That's the only discernible pattern is, assuming the coin's fair, you're going to get half heads and half tails. The non-pattern is you have no idea when they're going to show up. You know you're going to get clumps, which is what Vince was talking about, but his prediction is, after seeing 8 tails in a row, the coin's going to flip over to heads. It's ridiculous. It's 50-50. It could go either way on that next flip. The coin doesn't remember what flips, yeah? You see this all the time in casinos. People watching people play the one-armed bandits. Watch it. That machine over there hasn't paid out in a while. Watch it. She gets up, I'm gonna knock her off, I'm gonna take her seat. Then she gets up and people bum rush that machine. Stupid. It's absolutely stupid. The machine doesn't remember what it's doing. It's generating random numbers. Yeah? So it's amazing how the human element kicks in though, because we mistake the idea of a long-term percentage. Right? We mistake the idea of a long-term percentage. So say a machine pays out 1 every 1,000 pulls. Let's just say it does. Say it pays out 1 every 1,000 pulls, and you've watched that machine. 999 pulls and it hasn't paid out. Human nature says jump in because it's due. It's ludicrous.
It's so funny.
It's an average of 1 in 1,000. That doesn't mean it's going to happen every 1,000, huh? Just like this is an average of 1 in 2. Well, an average of 1 in 2, if you make that literal, goes heads, tails, heads, tails, heads, tails, heads, tails, heads, tails. Well, that's dumb. That's not what happens. It happens in clumps very often. You sometimes do get heads, tails, heads, tails. But way more likely don't get heads and tails in a row. You get those runs of certain ones. So that's why we have to make sure we understand what these numbers mean, what these fractions mean.
Well, it's like we learned with Monty Hall was, when you stay, your probability didn't change.
It's for 1 in 3.
Yeah, if you
Yeah.
switch, it does because, you're left 2 options to choose.
Which means, over time, if you stick with the door you started with, you're going to lose twice for every time you win.
Yeah.
Exactly. Nice connection, Benji. Nice connection.
Probabilities don't change with new.
They don't. The interpretation of them has to be done correctly, though. The trick with, and thank you for bringing that up, Benji, actually, because the trick with probabilities is understanding their limitations, too. Because the limitations of it are, when you're playing deal or no deal, or you're playing on the money, or you're playing let's make a deal, you get 1 shot. So the probability of a long run occurrence doesn't really apply because you get 1 shot at it. So what you do is you use the likelihoods and hedge your bets. You say, oh, if it's more likely that I win if I switch, then I'm going to switch. Because that's going to maximize the chance. It's never a guarantee. Remember the root of the word probability? Probably. Probable. Right? Probable. Probable doesn't mean likely. It just means you're measuring its likelihood. It could be very unlikely. For example, the chance of Max going into the store, grabbing 4 birds and coming home with 4 roosters, if they've been sexed as pullets. And that's what blew this guy's mind. This is why I developed the whole lesson around it in Matthew 43. Is that when the guy told me there's a 90% chance of a pullet being a girl, I said, that means there's a 1 in 3 chance I got a rooster in this box. And his jaw just like hit the desk. I was like, how do you do that? And I said, well, let's sit down. I got a piece of paper and I showed him the math behind figuring out that if each of those girls is 90% girl, which is essentially what it means, right? Every pullet is 90% girl, then there's a 1 in 3 chance that I've got at least 1 boy in that box. Turns out they were all girls. Also, turns out they're all molting right now, not laying eggs. Damn it. But nonetheless, they all did come out female. And that's what we spent quite a bit of time in 243 and 244 analyzing those. All right, so back to this. We got this. Did we talk about dice yesterday? I think we did. Single die, yes? Yes, because we spilled it to him bin. That was great.
Right.
That was fantastic. Actually,
Yeah, that's right.
Actually, let me go back to that in a second. What's the chance? I'm going to pick 1 number. What's the chance of rolling a 3 on dice? On a die. Not on dice. On a die. On a single die. Beautiful. What does it mean?
Every 6 times, there are 6 possible outcomes.
And they are all what? They're all equally likely.
And one of them is going to make you happy, and the other one's going to make you not.
Perfectly said, Benji, thank you. That's the classical or theoretical definition of probability. You list all the equally likely outcomes. In the bottom, that's your sample space. In the numerator is your event space. 1 makes you happy if you're betting on it, yes? 5 make you not. There's 6 total, so 1 in 6. Love it. Say it a different way for me. Say it a different way for me. Mike, go.
Yeah, 17% chance of negative.
Nice! Percentages, I like those. I like those a lot, especially when the fractions get unwieldy. Good, I like the percentages. Go ahead, keep somebody else, give me another one. I thought of you guys when I designed this last night. Here's a hint. There's a hint. I thought of you because I thought when David knocked the bin over, I'm like, I bet you I can model that in Excel. Because I'm a dork. What do you see up here, friends? Bunch of dice.
Randomly rolled.
Ready to spill them? There, just spill them. Just spill them again. Just spill them again. Just so you know, there are 6,000 dice in this sheet.
So
Incredibly
cool,
large
because the
number.
17% hardly.
Crystal has noticed when on 16, I'm gonna scroll back up. I think you buy the factor 6,000 dice.
17%. Well, like it's between 16 and 17.
So we said 1 in 6, which is between 16 and 17%. It's closer to 17 than 16. It rounds to 16.666%. So here we go. Rolling F9, rolling F9, rolling F9, rolling F9. What do you notice about the chance of a 3?
It stays between.
It fluctuates, yeah. But does it fluctuate far?
No.
Which means that what?
Probability is correct.
Well, it has to be.
Yeah, as a number.
It kind of has different than statistics, which is invented. Probability happens. So remember, what is it? What does the 1/6 mean again? Said a different way from using the 1 in 6 equally likely outcomes. I'll get you started. Over time.
You're gonna roll between 900 and 1,000.
Nice, good. Maybe even 1,100. Might go on the highs. I'm gonna stop right now. Let's look. Let's just go across like we did yesterday. Look for 3s.
What was the 2, 3? There's 1.
There's a clump right there, yeah? Yeah, going Canadian on you. Oh, there's one. You see what's happening? There are very often gaps. Like this 3 to this 3, there's a gap of like 10 dice, which breaks the 1 in 6. But then you've got like 2 3s right next to each other. So if you've got 10 between these two, but none between these two on average, that's 5 between 3s. And that's what we should see on average. On average, we should see 5 dice between each 3. That doesn't mean we're always going to see 5 dice, because that would be the opposite of randomness. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah? Do it again.
Still likely outcome.
How likely?
Very infinitesimal.
It's very, very small. Right. What Micah just said is if I roll a die 6 times, it's extraordinarily unlikely that I would go 1, 2, 3, 4, 5, 6. The odds are 1 in 720. But that's still possible. It's just not probable. Now the reason I can do that so quickly, and you can too, you just don't realize you can yet. Think back to your last project. Think back to your last project. I know you're trying to forget it. Okay. It's actually, no, I take that back. It's better than that. It's
best of 5 games.
It's 120 out of 6 to the 5th. Whatever that is, I can't do that one in my head though. And here's how I know that. You throw a die once, how many outcomes do you have? Throw a die again, how many outcomes do you have? Again. 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 So, your sample space for throwing a die 6 times is 6 to the 6th power. Don't bother computing that. Don't bother computing that. Don't worry, we'll calculate it all at the end. Okay, so, we're going to figure out the chance of rolling 1, 2, 3, 4, 5, 6. So we just grab a die and just throw the die 6 times and we get 1, 2, 3, 4, 5, 6. So your sample space, we just figured out, is 6 to the 6th power. That's humongous, yeah? 6 to the 6th power. Micah?
Can I ask you a really random?
Go, yeah. Perfect place for it.
Okay. No pun intended. Okay, on 6 rolls.
Yes.
What are the odds the same for going 1, 2, 3, 4, 5, 6?
Hold that thought.
All 6.
Let's come back to that. That's 120 times more likely, and I'll explain why momentarily. Actually, it's not. It's 720 times more likely. I'll come back to that. Let's answer this one first. So, if you roll 6 dice, how many ways can you roll? 1, then a 2, then a 3, then a 4, then a 5, then a 6? It's almost a trick question. So, in other words, if you have to roll that order, and you grab the die and throw it, what has to happen first?
1.
So you only have one choice for the first roll. Now what has to happen second?
2.
So you only have one choice for the next roll. What has to happen third?
3.
So you only have one choice. 4, one choice, 5, one choice, 6, one choice. Multiply all the ones together, it's 1 in 6 to the 6th power, which is essentially 0. It's essentially 0. It's not going to happen. But it is possible. It's just not probable. Yeah, just not probable. Now, Micah asked an interesting question, and this one blew my mind 2 terms ago in 243 because it actually happened. Remember that simulator I showed you guys yesterday with the pie chart generator? Where I bumped the F9 button and we just watched the pie chart fill out to 6 equal pieces? I always do that in 243 too, and I hit it 6 times exactly. Right? That gives me 6 rolls. Now, within 6 rolls, it's pretty unlikely that you're going to get each number exactly 1 time, which is what Micah just asked. Not rolling 1, 2, 3, 4, 5, and 6, but what's the chance of rolling each number once in 6 rolls?
Well, then, the first one with that is 100%.
We can do it this way. We're going to do it. I'm going to keep the theme going. Yes, you're correct, Benji. You're going to see your way happen momentarily.
Okay.
So here's the deal. What Benji just said is your first chance is 100%. That's because if you throw the die the first time, whatever happens, happens, yeah? Whatever happens, happens. Whatever number that you get, and then you start from that. So you've got 6 choices for the first roll, whether it's 1, 2, 3, 4, 5, 6. Now roll again. How many choices do you have now? You only have 5, don't you? Because you don't want to get that one again. If you want to get unique rolls, you don't want to get whatever you got here, you don't want to get a second time. So this is like the drunks and the coats. The first drunk goes in, grabs a coat, and leaves. Next drunk comes in, has to grab a different coat because the first coat took a walk. Now you got 5 choices. How about the next one?
4, 3, 2.
This kind of idea here is pretty cool in math. That's called factorial. You'll study it in 243. When you start at a number and multiply by every number down to 1, it's called a factorial. It's got a cool symbol too. 6, bang, over 6 to the 6th. So Benji, when you said, when you just correctly, you said the first one is 100%. That's this 6 over one of these 6s.
Because, yeah, it's like, things are going to make you happy. The first time you roll, of these 6 options you could get, one of them is going to be a number that you haven't seen before.
Yeah, right. But then you're limited as you go down. You're limited more and more and more and
On
more.
the first roll, all 6 options are ones you haven't seen.
Try it right now. Everybody grab 1 die. Roll your die once. Okay? So everybody's got a unique number, yes? Keep track of what you got. Roll it again. If you got a different number, keep going. Okay? If you got a different number, keep going. 1 and 6 if you got the same number. Good. Keep going to the 3rd number if you got a unique number on the 2nd. Who still has 3 unique numbers at this point?
Well, I did.
We're getting down to, we should only be 1 in 36 of you at this point. Yes, good, good. Roll again if you've got 3 unique numbers. Madison, you still going?
I got 5.
You got, Benji got 5?
Oh, man.
I did 4.
Hit the ground, count it.
No.
Okay, he's out. So nobody got 6 unique ones, yeah? Because there's only this chance of that happening. Swing back to the front, we'll get Google to tell us what that is as a decimal. It shouldn't happen. If it does happen, and it did happen in one day in 243 a couple terms ago. But you have to understand, I've been teaching math for 20 years. And I teach this course 10 times a year. So 20 times 10 is 200. Eventually, I'm going to see the result happen. I have to. It's what randomness is all about. I just don't know when it's going to happen. And then the kids are like, oh my God. But then they forget that they're part of a bigger puzzle. They're part of the puzzle of education where problems like this happen all the time. Let's do it right here, actually. Equals factorial 6 divided by 6 to the 6th. There. It's a 1.5% chance.
Yeah, that's way more likely than that.
Way more likely than the 1 in 6 to the 6th, which is that divided by 7. It's this.
Yeah.
Divided by 720. There. Point. The chance of going 1, 2, 3, 4, 5, 6 is 0.00002. 0.002%. That's not going to happen. Well, it is going to happen. It's going to happen 2 in 1,000 tries. I don't think we should keep doing it until we do it. I think that would be silly. Yeah, it'd be silly. But the point is that getting all 6 numbers happens 1.5% of the time. It's just that you don't know when it's going to happen. Right? Try it again. I'm curious. Try it again. Roll die 1 time. Okay, you mark what you get. Everybody's still playing. Everybody roll again. 1 in 6 of you are going to be done after that 2nd roll. Okay, Nick's out after 2 or 3, it looks like. To the 2, okay. 1 and 6 if you shoot me out after the first one. You see where I'm getting 1 and 6 from? Actually, you had it on your quiz, I believe. One of your quizzes, I think, has that question. Something like
Out of three.
out of 3?
If you get a 1.
Out with 3? Oh, Joe's still going!
I got a 1, I got
If you get a 1, he's on all 5. We got a 1, he's on the 5. Ah!
My first two numbers.
2, 3, 6.
And the problem with this is, it's actually much, much more likely to get all the way to 5 and then crap out on the last one. Because it's exponentially harder to get the one you need at the end. It's kind of like those commercials. I remember years ago, there was a commercial for Powerball where there's a guy at a party and there's a TV playing in the background and he's got his Powerball ticket. And he's like, oh, the Powerball's on. He pulls his Powerball ticket out. And you hear him go, oh, I got one of the numbers. And the guys at the party are like, whatever, one of the numbers. He's like, oh, I got 2. And they're like, yeah, 2. Everybody gets 2. And he's like, I got 3. And then you'll start crowding around him. And then he goes, I got 4. And then he goes, 5. And then the camera cuts. They don't show him losing because he didn't get the Powerball. Which happens exponentially more than hitting 5 of the 6 numbers because it's going to be hard to get that last 1 in 45 chance tacked onto the unlikelihood you already have. That's the beauty of it, yes? That's the beauty of it. Makes sense.
Because, yeah, real people will have that experience of getting
Of course.
a lot.
Now, Powerball is interesting in that it doesn't pay you. It doesn't just pay you for hitting 5 numbers plus the Powerball. You win in lots of different ways in that game. You win by getting just 3 of the white balls and no Powerball. If you get just the Powerball, you win. If you just hit the Powerball, you win like $2 or something along that,
Yeah,
$1 or
it's
$2. But and actually, this is why I asked you guys if you wanted to analyze that. But I think the mathematics is going to get too multiplicative, and it might drive you guys nuts if we do it now and next week. That's why. Let's focus instead on the dice you have in front of you. So here's what I'm going to do next. Let's talk about craps. Let's talk about craps. Let's shut this down. Oh, Joe, go ahead. Yeah, for sure. Fire.
Can you run the probability of 1 for the in the case 4, 5, 6, 1, 2, 3, 4, 5, 6 out of 7 rolls? What did I just do?
You just did it. So you have an extra roll. So what you have to do is you have to say, okay, the denominator is going to become 6 times 7.
Okay.
Then what you have to do, it's much higher than you think, and here's why. It becomes a Math 245 question, which is cool. I saw my buddy Doug Nelson who's teaching that class right now. The first thing you have to do is pick the positions of, let me swing this back over here. You first have to swing the positions of where the 6, 5, 4, 3, 2, and 1 are going to go. And this is going to sound weird to you. It's okay because I didn't get to it this term. We didn't have enough time quite to get to it. You have to pick the 7 positions. You have to pick 6 of them. All the 6 of the 7. Now
This
this,
is also in our project.
this-
the MHEH thing.
that's a permutation. This is a combination. This is an unordered order. Unordered order. So 7 choose 6 is the number of ways to drop that in. Now, this is just equal to 7. So you have to tap a 7 on there. Because you can have the 6 numbers that match anywhere you want. Yours happen to come in 1, 2, 3, 4, 5, and then 7, so you skip 6. But your question is, within 7, what's the chance of getting 6 and 1 extra that's 9? Okay? And then we have to multiply by 6 again, because now these represent the actual rolls on the die. Right. Somewhere in there you have to go 6, 5, 4, 3, 2, 1, and the last one can be anything you want. But then you multiply it by 7 because that's the number of ways to do it. So what it ends up being is 42 times more likely on top. But you have to divide it by 6. So the whole thing, if it's times 42 divided by 6, that's times 7, it'll be right around 10% of the time. Which is much more likely, it's 10 times as likely than it was before. Now that's a little high because I counted the case. And this is, you have to take this case out, I would think, where you go 1, 2, 3, 4, 5, 6, and you don't need the 7th roll. So arguably, you might be able to call this 6 and not 7 because you wouldn't count that one case. You see how annoying this is getting? This is why I don't do this in Math 105. Because as soon as I start getting the mathiness in here and the multiplication, I see students just go, oh, just roll this here. Yes, that's the whole point, is that I like the experimentation process. But Joe, it's a great question. So here, this is the chance of what you're talking about actually happening. What's nice about this mathematically is that divides off that, and it ends up being just 6 times more likely than that. So it ends up being 1.5 times 6, which would be 9%. There's the chance of that happening. It's still low, but it's nowhere near as low as it was with just 6 rolls. Because you lose your chance. Does that make sense? Yeah. Mm-hmm. Good, great question. Fantastic question. It's definitely a Math 245 question, just so you know. I just had my buddy Doug's teaching that class now, and he keeps asking me, like, What's a better way to explain a royal flush to people, or a straight flush, or four of a kind? I'm like, well, we play poker in class? It's like, we can't. I'm like, oh, that's right, you can't play poker in class. So then you have to break it down by the best ways, and this is the best way to enumerate any of those things, is just list out the possibilities like you did in your third project, and just go from there. It's about 9%. Higher than you think.
Yeah.
Higher than you think, yeah. Not as bad as 1.5. Now, let's study craps. Let's study craps. Start and stop again, or stop and start again.